X-rays were discovered by the Dutch physicist Wilhelm Röntgen around the turn of the 19th century, who performed much of his work in Germany. X-rays can be produced when electrons, accelerated through a large potential difference, collide with a metal target made, for example, from platinum or copper. Here we show an X-ray source, which consists of an evacuated glass tube, inside of which is a filament and a metal target. Through hermetically sealed electrical connections, current is sourced through the filament, and the metal target is placed at a high voltage with respect to the filament. The current in the filament causes it to heat up, and electrons escape into the vacuum. Once free from the filament, the electrons are accelerated toward the high positive potential at the target and collide with it. Through collisions on the surface and inside the target, the large kinetic energies of the electrons are dissipated through either atomic excitations or through collisional energy losses resulting in large magnitude decelerations of the electrons. Here we show a plot of the emitted X-ray intensity versus the wavelength. The plot consists of sharp peaks or lines superimposed on a broad continuous spectrum. The sharp peaks are called characteristic lines or characteristic X-rays because they are characteristic of the target material. The broad continuous spectrum is referred to as Bremsstrahlung, which is a German word for braking radiation, and is emitted when the electrons decelerate or break upon hitting the target. The characteristic lines are marked K-alpha and K-beta because they involve the n=1 or K shell of a metal atom. If an electron with enough energy strikes the target, one of the K shell electrons can be knocked out. An electron in one of the outer shells can then fall into the K shell, and an X-ray photon is emitted in the process. The K-alpha line arises when an electron in the n=2 level falls into the vacancy that the impinging electron has created in the n=1 level. Similarly, the K-beta line arises when an electron in the n=3 level falls into the n=1 level. A relatively large potential difference, on the order of 45,000 volts, is needed to operate an X-ray tube so that the electrons impinging on the metal target will have sufficient energy to generate the characteristic X-rays. Another interesting feature of the X-ray spectrum is the sharp cutoff that occurs at a wavelength of λ0 on the short wavelength side of the Bremsstrahlung. This cutoff wavelength is independent of the target material, but depends on the energy of the impinging electrons. An impinging electron cannot give up any more than all of its kinetic energy when decelerated by the metal target in an X-ray tube. Thus, at most, an emitted X-ray photon can have an energy equal to the kinetic energy, Ke, of the electron, and a frequency f equal to Ke divided by h, where h is Planck's constant. But the kinetic energy acquired by an electron in accelerating from rest through a potential difference v is E, the charge on an electron, times v, where v is the potential difference applied between the filament and the target. Thus, the maximum photon frequency is f equals EV divided by h. Since f0 equals c divided by λ0, a maximum frequency corresponds to a minimum wavelength, which is the cutoff wavelength λ0, where λ0 equals hc divided by EV. The medical profession began using X-rays for diagnostic purposes almost immediately after their discovery. When a conventional X-ray is obtained, the patient is typically positioned in front of a piece of photographic film, and a single burst of radiation is directed through the patient and onto the film. Since the dense structure of bone absorbs X-rays much more than soft tissue does, a shadow-like picture is recorded on the film. As useful as such pictures are, they have an inherent limitation. The image on the film is a superposition of all the shadows that result as the radiation passes through one layer of body material after another. Interpreting which part of a conventional X-ray corresponds to which layer of body material is very difficult. This is where the advanced X-ray techniques such as computerized tomography or CT scans dramatically improve the application of X-rays for three-dimensional imaging.